Cracking WPA2 is a solved problem. You capture the handshake, run it through Hashcat, and boom, you're in. It's fast, offline, and absolutely brutal. But here is what most people are missing. WPA3 was designed to make that impossible, and in many ways, it succeeded. But impossible and impractical are not the same thing, and in this lecture, we're going to prove exactly that. We're covering two real attacks against WPA3 networks. The first is an online brute force using a tool called Wacker. It goes live against the app, testing passwords one by one. The second is a downgrade attack. We trick a WPA3 client into falling back to WPA2, capture a classic handshake, and crack it offline with Hashcat. Both attacks are real. Both work in the lab. Let's get into it. Before we attack anything, let's understand what WPA3 actually changed. Because the attacks only make sense once you know what WPA3 tried to fix and where the gaps remain. On the left, the WPA2 problems you already know. The four-way handshake is capturable and crackable offline. There's no forward secrecy. Crack the password once, and every past session you recorded is decryptable. Deauth frames are completely unauthenticated, so you can kick anyone off any network at will. And the PMKID attack means you don't even need a client, just the AP beacon is enough to get something crackable. On the right, what WPA3 fixed. SAE replaces the four-way handshake. There's no crackable hash to capture anymore. Forward secrecy is built in. Each session generates a unique key that can't be derived from the password after the fact. MFP, Management Frame Protection, is mandatory. You can't just spray deauths anymore on a properly configured WPA3 network. But WPA3 is not unbreakable. Weak passwords and transition modes still create gaps, and those are exactly what we're going to exploit. The reason WPA3 blocks offline cracking is SAE, Simultaneous Authentication of Equals, also called the Dragonfly Handshake. Here's what actually happens. Step 1. Commit. Both the client and the access point independently derive a shared secret from the password using elliptic curve cryptography. Critically, neither side sends that secret over the air. They each compute it locally. An attacker listening in monitor mode sees none of it. Step 2. Confirm. Each side now proves it knows the secret without actually revealing it. This is a zero-knowledge proof. The AP proves it computed the same value, and the client proves the same back. If either side has the wrong password, this confirmation fails, and authentication is rejected immediately. Step 3. PTK. A unique pairwise transient key is derived for this session. Even if you use the same password 1,000 times, every single PTK is different. This is where forward secrecy lives. Step 4. Data. All traffic is encrypted with that session PTK. Past sessions are protected because their PTKs are gone, they were never stored, and they can't be reconstructed from the password alone. The bottom line is, SAE never puts a crackable hash in the air. In WPA2, the four-way handshake gave you a PMKID or an MIC you could attack offline. SAE gives you nothing. So if SAE blocks offline cracking, what's left? Two things. Attack 1. Online brute force with Wacker. You can't crack offline, but the app still has to respond to every authentication attempt you send it. Wacker automates those authentication attempts live, one password per attempt, directly against the real app. It's slow, it's loud, and it requires a managed interface rather than monitor mode. But if the password is in your word list, it will eventually succeed. Attack 2. WPA3 downgrade via rogue AP. This one is more elegant. Some APs run in what's called transition mode. They advertise both SAE and WPA2 simultaneously for backward compatibility. If you stand up a rogue AP with the same SSID but WPA2 only, a client device that supports both will fall back to PSK. You capture a classic WPA2 handshake, and now you're back to cracking offline with Hashcat. WPA3's protections are completely bypassed. Keep both of these in mind as we go through the steps. The conditions for each are different, and in a real assessment, you'll need to spot which one applies. Our first attack is brute forcing WPA3 with Wacker. The key insight here comes down to one thing: offline versus online attacks. With WPA2, you capture the handshake once, and you go home. You unleash your word list at full GPU speed, millions of candidates per second, completely disconnected from the target. The AP never even knows you're there. WPA3 shuts that down entirely. There is no crackable hash to take home. The only way to test a password is to attempt a live authentication with the actual AP right over the air. And that is exactly what Wacker does. It pulls a password from your word list, constructs a full SAE authentication exchange, fires it at the AP, and waits to see if it succeeds. One attempt at a time. This is going to be significantly slower than tearing through hashes offline. But pay attention to the critical technical note at the bottom. Wacker requires your Wi-Fi adapter in standard managed mode, not at the monitor mode. Step 1 is to identify the WPA3 target. We need to locate the network and grab the exact details Wacker needs to strike. First, back on Kali Linux, put your interface into monitor mode using sudo airmon-ng start WLAN 0. Next, fire up aero-dump-ng. Look at the output. We have a number of networks available, but the one we care about is Wi-Fi management. Look closely at the columns. Encryption shows WPA3, Cipher shows CCMP, Auth shows SAE. That right there is a pure WPA3 network. For Wacker, you need to note down 3 crucial details: the SSID, Wi-Fi management, the exact BSSID, which is the MAC address, and the channel. Step 2. Pull Wacker from GitHub and launch the attack. First, navigate to the Wacker GitHub repository and copy the URL. Drop back into your terminal and use git clone to download the repository, just like you see on screen. Next, move into the new Wacker directory. Before we can fire this tool, we need to give it permission to run. Execute the command change mode plus xwacker.py to make the script executable. From our reconnaissance phase, we gathered all the intel on our target, but remember the catch: Wacker requires the exact frequency, not the channel number. We know our target operates on channel 11. If you ever need to convert that, a quick look at Wikipedia's Wi-Fi frequencies confirms that channel 11 translates directly to 2462 MHz. Now, we have everything we need to strike. Now run Wacker with the details we noted. The full command is on screen. Let's break down every flag. -- word list is the path to your dictionary file. --SSID is the exact network name. --B SSID is the access point MAC address we noted from the scan. Interface is critically important. This is WLAN 2, a managed interface, not WLAN 0 MON. Frequency specifies the frequency. But the moment we run it, we hit a wall, an error. Here is why. Wacker relies on a very specific, custom build of WPA supplicant bundled inside the tool, and right now, your system doesn't have permission to execute it. We need to fix that before we can move forward. Drop back to the terminal and use the change mode command you see on screen to make that specific binary executable. With those permissions set, the roadblock is clear. Now, we are actually ready to fire. Now, run Wacker again. And there it goes. You can see it live, cycling through the word list. But expect this to be slow. Each attempt takes seconds, not milliseconds. This is not a tool you fire at a 14 million entry word list. You have to pick your targets and your word list carefully. And just like that, it hits the right one. We get the notification, password found. The Wi-Fi management network is cracked, and our password is chocolate1. Now, and this is incredibly important, we can now connect to Wi-Fi management with this password. But we never captured a handshake. WPA3's forward secrecy still holds completely. If you had been running arrow dump-ng, capturing all the traffic on this network before this exact moment, that captured traffic is still 100% unreadable. The Wacker attack gives you the password, and it gives you network access, but it does not give you the ability to decrypt past sessions. That is the fundamental difference from WPA2. Getting the password is no longer the same thing as getting the traffic. Now, let's see attack 2. The WPA3 downgrade attack. This attack exploits a real-world deployment problem. WPA3 is relatively new, and a lot of devices, older laptops, IoT hardware, legacy phones, only support WPA2. If an organization switches their AP to pure WPA3, those devices can no longer connect. The solution most access points implement is transition mode. The AP advertises both SAE and WPA2, at the same time. Modern WPA3 clients use SAE. Older WPA2 only clients use PSK. Everyone connects. But from a security perspective, transition mode is an exploitable misconfiguration. Because if the AP accepts PSK, and we set up a rogue AP with the same SSID, but WPA2 only, a client that supports both will fall back to PSK when it sees our rogue. We get a WPA2 handshake which we can crack offline. WPA3 is bypassed entirely. So, two conditions must be true for this to work. The AP must support transition mode, and MFP must be disabled. If MFP is on, our deauth frames are rejected and the client never disconnects. We'll verify both of these before launching. We will cover two methods for the rogue AP setup. In method 1, we will use host APD mana, which automatically captures the handshake in HCCAPX format. So, step 1 is the recon. So put your interface in the monitor mode using airmon-ng. First, scan all bands to find the target and note its channel. The -- band, a BG flag, scans 2.4 GHz, 5 GHz, and 6 GHz simultaneously. WPA3 networks often run on 5 GHz. Skipping this flag means you'd miss them entirely. There are multiple WPA3 networks here. For our demo, we will target Wi-Fi IT network that is on channel 11. Once we see the target, we lock onto it and write the capture to a file. This gives us two things, a PCAP file for Wireshark and a CSV file. Dump the contents of CSV file with cat command and look at the auth column. If it shows SAE+PSK, it means transition mode is supported, and that's our green light. Second thing we need to confirm is whether we can perform deauth attack against the AP. Now, open the PCAP in Wireshark and check MFP. Filter for beacon frames. Expand the RSN information capabilities field. If MFP required equals false, deauth attacks will work, and we're good to proceed. Alright, let's move on to method 1, which uses host APD mana. This is a modified version of host APD that is specifically designed to automatically capture handshakes from connecting clients. If you look at the left side of the slide, you'll see the configuration file we need to build. Every line here matters, but I want to draw your attention to the warning at the bottom. The channel selection is critical. The real AP is operating on channel 11. Our rogue AP must be on a totally different channel, in this case, channel 6. If you put the rogue AP on the same channel as the real AP, the attack will break. We're setting the SSID to Wi-Fi it to exactly match our target network. The mana WPA out parameter is the magic here. It tells host APD mana to automatically write the captured handshakes to a file in HCC/APX format. Finally, we force WPA2 and throw in a dummy passphrase. The victim doesn't need to authenticate successfully, we just need them to attempt the handshake. Let's switch over to Kali and actually run this sequence. First, let's create our configuration file. With our config in place, we'll follow the run sequence from the slide. Step 1 is launching the rogue AP. Run sudo host apd mana with our configuration file. Leave this terminal running and visible. Our rogue AP is up and listening. Now, we need to force the victim to disconnect from the real access point so they reconnect to ours. First, let's start monitoring our target channel with arrow dump ng so that the interface remains fixed on the specified channel. I'll open up a second terminal to handle the day authentication. Run air replay with the parameters as shown. We have provided it the AP MAC address and the MAC address of the connected client. Right now, the victim is getting kicked off the real AP. Their device immediately scans for the Wi-Fi IT network, sees our rogue AP, and attempts to connect, falling back to WPA2/PSK. When they do that, host APD mana captures the handshake automatically. Switch focus back to the first terminal running host APD mana, and you can see the captured hash right here in the terminal output. The last step is to copy this hash, drop it into a text file, and crack it. Copy the hash from the terminal. Run nanohash.txt, paste the hash, save, and exit. Now, run sudo hashcat-a 0-m 22000 hash.txt and specify the word list. And here we have our password. So, we have successfully forced our client to connect to our rogue AP and cracked the captured WPA2 hash. This gave us the actual password for WPA3 target network. Method 2 uses EAP Hammer as an alternative rogue AP tool. Same attack, different tool. We can launch EAP Hammer with a single command. Run sudo EAP Hammer -i-wlan1-c 6-auth WPA PSK -e Wi-Fi IT -creds. -i-wlan1 is the interface. Remember, this interface is in managed mode. C6 is the channel. -auth WPA PSK forces WPA PSK mode, which triggers the PSK fallback from dual mode clients. -creds tells sudo EAP Hammer to capture credentials and handshakes from connecting clients. Step 2. In a separate terminal, lock your monitor interface onto the real AP's channel so you can see its clients. In another terminal, deauth the client from the real AP. Same as we did in method 1. Once the victim connects to our EAP Hammer, rogue AP, the handshake is captured and written to a .cap file which we can see in the terminal. To crack the handshake, we can either use aircrack or hashcat. First, copy the handshake file to the current directory. Now use aircrack directly with a dictionary. And you can see that aircrack is working on it. That's it, our password is cracked. If you want to speed up the process, you can use hashcat. But first, we need to convert this file. Use HCX #2cap tool to convert the captured handshake to PCAP file. Now, use HCX PCAP-NG to convert the file to 22,000 format for hashcat. We can now use hashcat as shown to crack our password. And we will get our password in a few seconds. That's both WPA3 attacks covered. Pure WPA3 networks are still vulnerable to online brute force if the password is weak. Wacker automates the SAE exchange live against the AP. Slow, but it works. But if the AP runs SAE+PSK transition mode and MFP is disabled, you can force a WPA2 handshake from connecting clients and crack it offline at full speed. That's all for this lecture. Have a nice day.